Hi students, in the last session we have discussed about conductometry. In this session, let us discuss about potentiometry. So the type of question asked on this is explain the theory, instrumentation and applications of potentiometry. So let us take the theory of potentiometry here. So potentiometry is also one of the electroanalytical techniques as we have categorized in the first session, in which the amount of a substance in the solution is determined either directly or indirectly from the measurement of the EMF between the two electrodes that are dipped in the solution. When a metal M is immersed in a solution containing its own ions M power n plus, the electrode potential is given by next equation from the first session. So what is the next equation here? E is equal to E plus E naught plus 0.0591 divided by n into log of m power n plus. Then what is E and what is E naught? So E can be measured by combining the electrode with a reference electrode and measuring the EMF of the cell using potentiometer. The concentration can be calculated provided E naught value of the electrode is known. So here E can be measured by combining the electrode with a reference electrode. So, and the measuring EMF of the cell using potentiometer. Here, E naught cell is provided by electrochemical series. So that is why E can be measured. E can be measured using potentiometer. Then, so after this, the electrode whose potential is dependent upon the concentration of the ion to be determined is termed as indicator electrode. So in this potentiometry, there are two electrodes are used. The electrode whose potential is dependent upon the concentration of the solution to be determined is termed as indicator electrode. And the electrode whose potential is independent upon the concentration of the solution to be determined is a reference electrode. So here the indicator electrode responds to the change in concentration of the unlike species present in the solution. So for this to measure to make the EMF of the solution, a potentiometer is used. So next here, the EMF of the solution containing the initial solution is determined and relatively large increments of the titrant from the burette is added until the equivalence point is reached. The EMF is determined after each addition. Suppose, for example, 0.5 ml, 0.5 ml, we are going to add. So the approach of the endpoint, when you keep adding the titrant to the solution, the approach of the endpoint is indicated by somewhat a more rapid change in the EMF value. Sudden jump occurs in the EMF value. So in the vicinity of the equivalence point, vicinity means a critical endpoint. Vicinity of the endpoint means a critical endpoint. So that is why in the vicinity of the equivalence point, equal increment should be added. Sufficient time should be allowed after each addition for the indicator electrodes to reach a constant potential before the next increment is introduced. So that is why here, before going to add next addition, sufficient time should be allowed for the indicator electrode to reach a constant potential. So next several points should be obtained well beyond the end point. So after getting jump, several points should be obtained. So here from this we can plot the graph or we can locate the endpoint of the titration. How to locate the endpoint of the titration here? The important factor in a titration is the recognition of the endpoint. So the equivalence point or endpoint of a titration can be fixed by examination of the titration curves, including derivative curves. So there are two ways to fix the endpoint by examining the titration curves. Second one is derivative curves. So here, when you take titration curve, the titration curve can be obtained by plotting EMF readings obtained with the reference electrode and indicator electrode pairs. So against volume of the titrant. So that is why when you take here, so EMF values, whatever the EMF values you get from the potentiometer, you can take on y-axis, and volume of titrant added from the burette is taken on x-axis. You get a S-shaped curve like this. So from this S-shaped curve, you can observe here. So it locates, it indicates an approximate endpoint of this titration as being midway along the steep portion of the curve. So it gives only an approximate endpoint of the titration or equivalence point of the titration. So as being midway along the steep portion of the curve. That is why in order to get to precise endpoint, we have to go for derivative curves. So including second derivative, third derivative curve. That is why when you do calculation for potentiometry, you are going to plot like this curve. You get a bell-shaped curve. So that is why this is first derivative curve. This is first derivative curve, and this is second derivative curve. First derivative curve for potentiometric titration, and this is second derivative curve for potentiometric titration. That is del square E by delta V square. So you generally we use this first derivative curve for potentiometric titrations, so that we can calculate the amount of substance present in a solution. So when you take delta E by delta V values on y-axis and volume of titrant on y-axis, you get a bell-shaped curve like this. And from peak to, if you make a dotted line to x-axis, you will get the equivalence point of the titration here, or end point of the titration here. Then moreover here, second derivative curve for potentiometric titration. So you are going to take del square E by delta V square on y-axis and the volume of titrant added on x-axis. You get a first derivative curve like this. So this indicates the end point or equivalence point of the titration. So that is why here what we can discuss, an approximate value of the end point can be obtained from the first graph. So as being midway along the steep portion of the curve as shown in the graphs. So hence, the endpoint can be located more precisely by employing derivative curves, in which the first derivative curve is taken delta E by delta V versus volume of titrant, or the second derivative curve del square E by delta V square against volume of titrant added. So from these two graphs we can locate the endpoint more precisely. So next after this instrumentation. So what is the instrumentation and setup? What is the instrumentation setup we have to use for this potentiometric titration or potentiometry? So here a potentiometer consists of an indicator electrode. So look at the diagram here. So indicator electrode. This is the indicator electrode. So generally we use platinum electrode or ion selective electrode, that is glass electrode, as an indicator electrode. Indicator electrode means which responds the ions of the unlight solution, whose amount to be determined. That is unlight solution. Next, a standard reference electrode, that is calomel electrode, obviously we use, or silver chloride electrode we use as reference electrode to maintain the potential constant during the course of titration. Then this is potentiometer. These two electrodes are connected by a potentiometer, and titrant is like in the titration of FAS versus potassium dichromate solution. Potassium dichromate solution is taken in a urate, that is as titrant. So this is titrant. So this is the instrumentation setup for the potentiometry. So next, so what are the applications are there for potentiometry? So there are n number of applications are there for potentiometry. So let us take number one is oxidation reduction titrations, which you are going to do this experiment in our chemistry lab. Oxidation reduction titrations. So here oxidation reduction titrations can be conveniently be carried out as potentiometric titrations. For example, in the titration of Mohs salt solution, that is FAS solution with potassium dichromate solution. So calomel electrode is used as the reference electrode, as you see in the diagram, and inert platinum foil is used as an indicator electrode. So which is actually the oxidation reduction electrode involved in the redox species present in the solution. Actually, platinum electrode is used as an indicator electrode in this experiment. So how to do this experiment actually? Before the titration is started, the solution contains only ferrous ions in the solution. When you take FAS in a beaker, so FAS contains only Fe2 plus ions in the beginning. So that is why when a small amount of dichromate solution is added to the beaker, so equivalent small quantity of Fe2 plus ions are converted into Fe3 plus ions in the presence of chromium 6 plus ions, because you are going to add potassium dichromate solution, K2Cr2O7 solution. So that is why Fe2 plus ions are oxidized into Fe3 plus in the presence of potassium dichromate solution. Now, here, in the presence of chromium 6 plus ions in dichromate are reduced to chromium 3 plus ions in the process. Okay, though it acts as an oxidizing agent, so chromium 6 plus ions get reduced to chromium 3 plus ions. So here, the reaction takes place is, see here, when you add chromium 6 plus, that is potassium dichromate to the FAS, Fe2 plus ions are oxidized into Fe3 plus. In the process, chromium 6 plus ions gets reduced to chromium 3 plus ions. So here, uh, actually, the presence of Fe2 plus ions and Fe3 plus ions in the solution, when you add K2Cr2O7 solution, then gives rise to an oxidation reduction electrode, the potential of which can be picked up by the platinum electrode dipped in the solution. So already platinum wire is dipped in the solution. That is why here. So in the beaker now both Fe2 plus and Fe3 plus ions are there. So Fe2 plus is reduced species and Fe3 plus is oxidized species. So both of them forms a single electrode with platinum wire. So the electrode potential of the so formed electrode is given by this uh, Nash equation. That is E is equal to E naught plus 0.0591 into log of Fe3 plus divided by Fe2 plus ions. So that is why here. So whatever the potential developed in the solution is picked up by platinum wire. So next year, the electrode potential of the indicator electrode, that is platinum electrode, depends upon the ratio of the concentration of Fe3 plus and Fe2 plus ions, as you see in the equation. The potential of the indicator electrode depends upon the ratio of Fe3 plus and Fe2 plus ions in the solution. So as the titration proceeds, the concentration of Fe3 plus goes on increasing, that of the Fe2 plus goes on decreasing. That is why, as a result, the ratio in the expression for electrode potential goes on increasing, and the increase in the value of ratio becomes very large near the end point. This amounts in the large increment in the electrode potential and in turn in the measured EMF of the cell. So that is why here, when it reaches the equivalence point of the titration, the ratio becomes very large. This ratio becomes very large. So this amounts in the large increase in the potential, in turn the measured EMF of the cell also. That is why it gives a greater jump at the equivalence point of the titration. So at the equivalence point, all the Fe2 plus, at exactly the equivalence point, so what happens? All the Fe2 plus ions are converted into Fe3 plus ions. Then the platinum Fe3 plus Fe2 plus electrode ceases to exist. So once Fe2 plus ions all are completed, then the Fe2 plus, the platinum Fe2 plus comma Fe2 plus, so electrode ceases to exist. So no more, as no more Fe2 plus ions are present, then the indicator electrode ceases to exist. So that is why, which along with here, but the addition of excess of dichromate introduces the chromium 6 plus ions into the solution. Actually here, so one seizes the Fe2 plus ions in the solution. So addition of excess of dichromate solution introduces chromium 6 plus ions along with chromium 3 plus ions. That is why it forms a new oxidation reduction electrode with platinum wire. That is platinum bar, chromium 6 plus comma, chromium 3 plus. So that is why it forms one more single electrode with chromium 6 plus and chromium 3 plus, okay, ions. So this changeover of the indicator electrode from iron to chromium at the end point also contributes to the large increment in potential at the end point of the E naught values of the two electrodes. So why it gives means the E naught values of the two electrodes differ by a large. That is why it amounts a large increment in the EMF value at the equivalence point of the titration. Then, so afterwards here, second application of this potentiometric titration is precipitation titrations. Precipitation titrations. So precipitation reactions can also be carried out potentiometrically. So in the precipitation of halide ion, for example, chloride ion, from solution by the addition of a suitable reagent like AgNO3, the concentration of halide ion in solution will change most rapidly in the region of the endpoint. So that is why here, so the concentration of halide ion in the solution will change most rapidly in the region of the endpoint. So the potential of an indicator electrode responsive to the concentration of halide ion will undergo a like change and hence can be followed potentiometrically. So as the titration proceeds, what will happen? The concentration of halide ion changes. So according along with that concentration, then the indicator electrode also responds. So that is why here the potential of an indicator electrode responsive to the concentration of halide ion and will undergo a like change and hence can be followed potentiometrically. So in this case, an indicator electrode comes in equilibrium with one of the ions of precipitate. So that is why here, for example, when you take AgNO3 plus NaCl, then silver electrode is taken as an indicator electrode because silver electrode can come in equilibrium with either silver ions or chloride ions. So that is why, for example, in the titration of silver ions with a halide ion, silver electrode can be used as an indicator electrode. So this is one of the application of potentiometry. Precipitation titration. Precipitation means precipitation is done during the titration, and moreover, we can calculate the normality of either NaCl or AgNO3 solution. In turn, we can calculate the amount of NaCl or AgNO3 solution present in a given unknown solution. So this is about potentiometry theory, instrumentation, and any two applications of potentiometry. So thank you.